Well, ladies and gentlemen, welcome to our annual meeting and our annual speaker, Faith Morrison. Many of you know, I'm sure all of you know. Uh, if you read the last newsletter, not the one just out, but the one before, you'll also know she was a founding member of the Friends of the Michigan Tech Library. She's been with us from the beginning, and we hope for another 25 years or more. We're gonna keep you working for as long as we can and enjoying every minute of it. On a more professional note, Faith was a professor of chemical engineering and just retired last year, at the end of last year, from Michigan Tech, and is already enjoying retirement. I see her and her husband Tom out walking far too early on the hills in East Hancock each morning. Her field I don't know if you're going to still work on this, but her field was polymer rheology. And so she's a rheologist, I suppose. For those who don't know what that is the science of the deformation of flow of matter. That is how molecules slip past one another, often in confined spaces. So no doubt to an earlier generation, she would have made great success talking about the Play-Doh Fun Factory. And I suspect that even students today would understand it in seconds. Certainly if she was teaching it, they would understand it. FYI, and because this is a library group, I looked it up for the fun of it. The term rheology was coined in 1920, but based on ancient Greek aphorism by Simplicius, everything flows, or periria. So there you go. You may also not know that Faith was a tireless educator and worked on the pedagogy of engineering and received numerous awards from both the university and her professional societies for that, as well as her work itself. She also, in 2015, received the Distinguished Service Award from the Society of Rheology, which I suspect was a wonderful crowning achievement to a career well spent. But in honor of our topic today, or rather the timing of our topic today, I thought I'd ask the question, what can we do with pumpkins? And in particular, what can we do with pumpkins in Faith's area of expertise? Well, Google, of course, gives us lots of answers. If you Google around, it turns out there are all sorts of things on pumpkin physics one can do at this time of year, usually for extra credit. But more importantly, for pumpkin rheology, get to the thing we're forward. Yes. What happens when a pumpkin goes splat? I suspect Faith could tell us. On a more serious note, there are actually, believe it or not, articles on pumpkin rheology, or at least the rheology of pumpkin flour. And we can ask Faith to explain these diagrams later because I haven't a clue what's going on there. Better yet, it's really frankly quite boring. You could watch a video of pumpkins being shredded into a composter, pumpkins flowing through a confined space, more things on pumpkin rheology. But I think where we really want to end here are with little pumpkin squishies, which allow you to stretch and twist and skew them for your joy at Halloween time. And if that isn't appropriate for this, I think the final picture is officially you can get an easy pumpkin squish bag, toddler approved. I'm sure that Faith will talk to us considerably more seriously about uncertainty in analysis in engineering science and perhaps tie it back to pumpkin squishing. Take it away, Faith.
Well, thank you, Steve. That was a huge surprise and really a lot of fun. Yeah, I was in fact, president of the Society of Rheology for 4 years. And not everything he said about rheology was absolutely correct. I'm not an expert in pumpkin rheology, but clearly if you drop the pumpkin, it would deform and create some kind of a flow or another. Yeah, I have really enjoyed my time studying rheology. And in fact, in my research, which is experimental work, we do come across the problem that's the subject of the talk today, which is related to my third book, which is on uncertainty analysis. So what I wanted to share with you today is just a not too technical introduction to why I thought it was important to produce such a book, and how all of us, and in fact, in my opinion, how society in general could really benefit from some reflection and then ultimately some quantification on uncertainty in numbers that we use for important decision making. So I'll be talking about some subjects that are part of my book, and Steve already put up the picture of my book, but I'll put that up again, available on Amazon and in paperback. And then, of course, I'd love to answer any questions that anybody has. So my talk is I titled "Facing the Data: Managing Our Confidence in What We Measure," so that I could frame this very scientific subject of uncertainty analysis or error limits a little bit more generally for today's talk. So I was telling some friends that when I start a talk or a module in a course or a course in itself, I always, starting is the hard part. I don't usually start with "it was a dark and stormy night," although that's a classic cliche way to start things. But I really go back to the beginning. And when I was thinking about how to introduce to you the importance of uncertainty, I came up with this classic philosophical question: how do we know what we know? So how do we know many things that we build on and move forward in our lives and discussion? And where did we get that knowledge? And so when I was preparing our talk, I came upon this quote from Albert Einstein that I thought really nailed it. And this really goes back to the Reformation and to the Enlightenment period, when mankind was turning from just accepting truisms to establishing truisms based on what they observed in nature. So this ultimately comes to Einstein's era, which was the early 1900s, and his statement, which is that simply sitting around and thinking, even thinking well about a subject, doesn't produce knowledge in and of itself. But if you start with the things you observed, empirical things, and things that you measure, then you have something to think about, and then you can build knowledge. So Albert Einstein uses this characterization of the world as the empirical world, and empirical means, if you ask the Oxford English Dictionary, it's based on or concerned with or verified by experience or observation. So it comes right down to experimental measurements. In fact, in French, the word for an experiment is expérience. So experimental measurement is what defines the real world, the empirical world. And all knowledge, according to Einstein's statement here, of reality starts from experience and ends with it. And I find that that resonates with me, that what I'm going to be talking about is that people can have opinions, and people can have framings of ideas. And I'm not saying that in a judgmental way, one way or the other, about whether or not I agree with anybody's framings or opinions. Those are all fine things to have. But if you're going to think about something and really learn about knowledge, about what really happens, it's tied to what is observed. So that's how we know what we know. We measure it. So I am going to be talking about measurements and, in fact, the quality of measurements. And so quality is a nice positive word. The opposite of quality is uncertainty or error. So that if there is a lot of error, it's of a low quality measurement. But nevertheless, we have to give it a shot, and we have to try to measure something. And there are some uncertainties that are built intrinsically into any measurement. And I'm going to talk about 3 categories of uncertainty through my 3 examples here today. So let me get a little specific, because it's a little bit high-minded, starting with how do we know what we know. So I just want to start with an example and say, for instance, if I sew, which I used to, you often have a big pile of fabric, and you might ask yourself, well, do I have enough of this to make something out of it? How much fabric do I have? So that's the first example I'd like to talk about. And I'm going to stand up here and show you how I was taught to do this when I was a student. And so I have this load of fabric sitting up behind me here. So here's the fabric that I showed in the video right here. I found it in my attic. And it's a piece of fabric. And when I was a young student and learning how to sew from my mother, and then subsequently from some teachers in school, they taught me this little heuristic. They said, okay, so if you want to know how many yards you have, raise it up like this. And this is about a yard. Okay, so this is about 1 yard. And so we would always just ballpark all of our fabric. So that's 1 yard, that's 2 yards, and 3, and 4, and 5. And then a little bit more, maybe 5¼ yards of fabric. So that's a rule of thumb or a heuristic for a measurement. But does it work? And the answer to that is, well, we can calibrate the measurement. So here's a measuring device. This is a yardstick. Okay, so this yardstick allows me to calibrate that little measurement. I can say that, okay, when I go from the tip of my nose to my fingers out here on my left, there's about a yard. So as long as when I just did that experiment, I kind of put my head about here, it's going to be accurate. So the mapping of a measurement of something that I trust, in this case, a yardstick produced by some manufacturer, and the measurement that I'm actually going to use, the device or the technique that I'm actually going to use, this very casual one, which is very handy when you're making your way through a lot of fabric. I'm calibrating it by making sure I understand that this is how my head should be when I do this measurement. And if I have a little bit shorter arms, I might have to do that a little bit more to the right. If I have long arms, I might do it a little bit more to the left. So that's just sort of a folksy idea about calibration. And all devices that give us a number also have to be calibrated. So that is the first sort of issue that comes into finding out about the accuracy of a measurement made with a device or a technique is calibration. So the formal definition of calibration is a step made to establish the correctness and utility of a device. So I had a device or technique. I had this measurement technique that worked, I hope. And then I had to calibrate it against a standard. So a standard is what the word means. It's a device used whose correctness or properties are known. But even the standard can only be correct to a certain level. That meter stick or that yardstick that I have is correct, but it's not able to measure down to a micron stage. It's marked in eighths of an inch, and maybe 1/2 of an inch might be the limit of its accuracy. So that's the standard I use to calibrate my technique. And then the unit under test or the technique under test is the thing that's being calibrated. So all these background steps that we don't think about too much when we make a measurement are nevertheless have a strong impact on the accuracy of the measurement. So the last line on my slide says that the results from a unit can't be more accurate than the standard used in calibrating the device. So there's no way that I can take this device of measuring yardage of fabric and get the length of that fabric to a 10,000th of an inch. The device I calibrated it with is not good to that level. So this is one of the things that I emphasize to my students in my laboratory class, is that even though your calculator or the device display may show 7 or 8 digits, that's not how accurate that device is. There's a lot of inquiry that we have to do to figure out really how accurate we should record the number as being. And one of the primary issues is this issue of calibration. So one of the things I developed in my book was a set of worksheets to guide students through the kind of questions one should ask if one wants to interrogate the quality of the data, the quality of the measurements that we make, so that we can identify where the limiting conditions are. So this is my worksheet, and I'm going to pull one out here for you and right on it for the example that we just gave. So if I grab a copy of the worksheet, which I have here. Okay, so here's my worksheet, and I got my camera out of whack while getting ready here. So I'll zoom in here a little bit. So this is that same worksheet that I showed a second ago. There we go. So this is the calibration worksheet. And one of the things that I advocate in providing these worksheets is that this becomes a record that once you've, as a person making measurements with a device or a technique, you can hang on to these worksheets once you've thought them through. And then every time you use this technique or device, you've already done the thinking, and you're going to be able to figure out how accurate your device or technique is. And in addition, and I make this point as well, if you find through using these results that you may have overestimated or underappreciated something, you can always go back and ask yourself, well, what did I do to come up with the estimates that I had, and can I improve on them? So these are all on the web, by the way, on the previous slide, and I'll put that up again in a second. That people can download these and use these freely. So this is the guiding of us through this calculation for doing the fabric yardage that I just did an example of. So I'm going to just name it so I can find it later. And I might call this the fabric yardage. And it was about 5 1/4 yards. And then these are explained in more detail in the book, and I'm not going to be able to explain everything in the time length that I want to make my talk today. But these are the 3 things that we're going to consider. The first one is a rule of thumb that I discussed, that if I report a number and I say 5 1/4, I can hope that it would be accurate all the way down to the last digit that I've been supplied. And this is something that will be pertinent with something read off of a meter where there's some number. You can say, well, the last digit's the last one I know. Maybe it's accurate down to that last digit. For most calibration devices that you buy and use, it's the manufacturer who does a very rigorous job in calibrating the device. And they always publish these calibrations. And so I talk about that, like how to find these with the internet. It's much easier than it used to be, but it does take some time to interpret that calibration. But when you have something like the yardage technique that I just introduced, that's not applicable. So that one I'm not going to consider. And the third method is you could calibrate it yourself. Okay, so that's what I did do. In fact, I got that yardstick and I calibrated myself. So that means I'm going to say that I think that's probably, my estimate is probably about to 1/8 of a yard. So I'm going to say, just off the top of my head, using my own common sense, that if I were reasonably careful with that little technique, that I might be able to get the yardage to within about 1/8 of a yard. Now you may be thinking, that's pretty optimistic, Faith. I saw you moving your head to the left, move your head to the right, and that's fair enough. So maybe you would pick 1/4 of a yard just to be safe. Or maybe you thought, yeah, you weren't careful, but I would be if I did this. I could get it to 1/10 of a yard, or even better. That's up to you. And I'm going to talk a little bit later about this idea of judgment and how that feeds into things. So there's some language here about 2ES. I'll talk about that a little bit more in the future. But this 2ES becomes the error bars on your answer. So my answer here is going to be 5 1/4 yards plus or minus the largest of the 3 here. So 0.125 yards. I can calculate ES, which again, I'll talk about a little bit in a second or a little bit later. And of course, 2ES is picking out which of these is the largest. And I end up with a way to answer the question, what is the length of that fabric sample, and how precisely, how accurately do I know that? Okay, so that's the worksheet, and that's how I filled it out for this particular case. So I'm going to go back now, if I can get There it is. I'm going to go back to the other part of the presentation. And here are the measurements that I just wrote now typed in. And we've been guided to an answer to how well we know the length of that fabric. So this is my summary of the calibration idea. There is uncertainty in our measurement of the length of this fabric, and this is caused by intrinsic limitations in the instrument or technique. So the technique could be made more precise, more accurate. Precision and accuracy are not the same thing. I won't divert into that area, but it's neither, in this case, neither precise nor accurate. But there are limitations. And we talked, guided by the form, about the 3 types. And in this case, it's the user calibration that determined the accuracy, and it's calibration error. So that's one of the 3 limitations that I want to talk about. But it's not the only thing that can limit the quality of a measurement. So let's try another one. And so a second one might come from measuring the length of an object. So I just picked a leaf from the tree in my front yard. It doesn't look like that flowery version just right today because it's October, but that is my tree in the springtime. It's a tulip magnolia and has beautiful pink and white flowers that come out before its leaves come out. And then green leaves come out. And even as late as October, we have green leaves on the tree. So if I want to know for just one particular leaf, excuse me, how large the leaf is, I'm going to have to measure it. So I'm going to go back to showing you how I'm going to do that. So here's the leaf. And if I want to know the length of this leaf, I'm going to take a measuring device, my ruler that's measured in centimeters or millimeters. And I'm choosing my standard. It's a little bit arbitrary, but I want to know the length from where this stem meets all the way to the tip of the leaf. And if I look carefully here, I see that it's about 130 millimeters long. So I can write down that length, but I think you'll agree with me that the accuracy does depend on this device itself as well, this ruler that I'm using. When I read the ruler, this particular ruler is only marked in 1 millimeter increments. And I have some ability to estimate a length that lands between 2 marks, but it's limited. So there is a limitation to the accuracy with which I can actually take a measure of leaf length. And in the case of leaf length, there's what's called reading error. Okay, so this is the reading error worksheet. So in the case of the reading error, because I think of these devices as ones I'm going to save, I have the name here. I'm going to name the length. And I found that it was 130.0 millimeters long. And then for reading error, there are coincidentally 3 types of questions one can ask to see what kind of errors result from the ability to read from the device. And the first one is called sensitivity, and it doesn't relate to this case, but sensitivity has to do with whether the device can sense something. So maybe you've used devices and seen that sometimes they give a reading of 0. They don't seem to be able to sense the pH, or they don't seem to be able to sense the temperature because it's off the scale of the device, or the weight. So if you took your bathroom scale and put a pen on it, it would say there's no pen on the scale because it can't sense it. So there's a limit. So if you put heavier and heavier things on the scale, you could figure what the limit of sensitivity was for your scale. And so there might be a limit to the sensitivity of this ruler, but it's smaller than the other things I'm going to talk about. So really, sensitivity is not applicable in this case. But for any other measurement, it's worthy asking about sensitivity. There's a second one, which is resolution, which is very straightforward. So on this device, there's a smallest division. So the smallest division is 1 millimeter, and half of that is half the smallest division. So that's the standardized definition of resolution, is how resolved is something like the scale on the measurement. So that one's really pretty easy. And a third issue that's dealing with the reading is fluctuations. So for those of us who've used analog devices, we're used to seeing maybe a little needle on the device that just sort of chatters. It's just, maybe your speedometer on your car would sometimes chatter. So if you have a device, a pressure gauge, or something with a needle on it, it can easily chatter. There are also times when you put, even on some types of weighing devices, you can put a weight on there and you can watch the number go 4334 or 43434, and it kind of moves between two numbers. So those are the fluctuations that can also affect the accuracy of the reading from that device. So again, that's not an issue here with this reader. It's not fluctuating, so I'm going to say that's not an issue here as well. So as I do explain these all in the book, but again, only the biggest of these three is important. So 0.5 millimeters is the raw reading error, and we can work out what the impact of this reading error is, and it's related to a statistical distribution called the rectangular distribution, and it's related to the standard deviation of the rectangular distribution. But there's the formula for the result. You take this number and divide by √3, and you put that in your calculator, and you get 0.29 millimeters. And the appropriate 95% confidence interval, and I'll talk about 95% confidence again in a bit, is this 2 times this standard error. So I double this and I get 0.6. And I end up saying that the length of my leaf is 130.0, what I measured, plus or minus this 2ES, 0.6 millimeters. So it's a very standardized kind of methodology that moves us through questions that we might not bother with if we're just given a ruler and told to make a measurement, and we wouldn't really be able to say, how do I know that I'm doing this right? How do I know that this is really the accuracy of what I'm doing? So there's a bit of rigor behind this, but it can also be relatively straightforward to do. So for reading error, as in this example, there's sensitivity, resolution, and fluctuations are 3 major contributions to uncertainty that resolves from instruments and techniques with finite reading values. And in this case, we have our result. So the last one is actually the one I lead with in my book, which is replicate error or statistical error or random error or stochastic error. So I find that statistics moves very quickly into a heavily mathematical domain, but actually it's a super important aspect of understanding how we know what we know, because it's a big statistical error or unknown influences on our measurements are an important part of the uncertainty. So my example for this is blood pressure. I take my blood pressure every day because I have to monitor some aspects of my heart. And I always take a triplicate. I always take 3 measurements in a row. And I'm going to explain why I do that. So here's my third example. Do I have high blood pressure? And you're probably a little bit familiar with blood pressure. There's always something like 120/80. So the upper number is called the systolic blood pressure. The lower is the diastolic. And those numbers have units. It's millimeters of mercury, which has a historical reason behind it that's kind of interesting. So this is my left arm, and this is my blood pressure device here. So what happens when you take blood pressure for yourself? Like when you go to the doctor's office, they take it once and they write it down. But if you take it for yourself, you find that you don't get the same number if you do it 3 times in a row. So it matters. And if you Google it, like like what impacts my blood pressure? If you don't sit up straight, if you cross your legs, they say, oh, don't cross your legs. Put your legs flat on the floor. Relax, but sit up straight. Those are kind of contradictory. They don't say this very often, but you really should clear your mind, because if you start thinking about somebody at work that really irritates you, your blood pressure goes up. So, and then there's things happening that you don't really understand that might be going on, like how recently did you eat, or all kinds of things that you could hypothesize that kind of distracting you in a way, because really you just want to know what your blood pressure is. So this is very common. It's very common that you're trying to take a measurement and it won't stay put. Like when you look at the meter, it stays put. It says what it's reading for the last meter. So the one that's shown there, 106/82, that's not chattering. That's not fluctuations. It's not a reading error issue. But if I take 3 in a row, and these are real data, if I take 3 in a row, one time I get 113/89. That 89 is a little high. One time 104/83. That's pretty good. And one time 106/86, and that's somewhere in the middle. So that's a little confusing. So which of those numbers should I use? So when you have influences on your measurements that come from effects that are seemingly coming out of nowhere, they're random, you can't say what they're from. If you know what they're from, and you should fix that if you can. And that's a systematic error. And that is a part of experimental work, is figuring out what is causing your numbers to move around and not to be reliable. And that is a big part of being an experimentalist. But when the numbers just have this, what we call stochastic character, where they don't exactly come out the same time every time, but they're still reasonably representative of the thing you're trying to measure, then if they are sort of neutrally random, then you can get a good estimate of what the true value is by just averaging the values. So the average, this X bar, is the math symbol that is adopted for the average. The average of your stochastic measurements is a good estimate of the true value of the variable. So we know how to take an average. We would add 3 numbers up, divide by 3 if we had 3 measurements. So that's fine. The uncertainty is now a different story. So the average, the number I'm going to say is the one number, is going to be the average. But how am I going to get this uncertainty that I've been using in my other 2 examples, the 2ES? And how, and is she ever going to explain this 95% confidence business? Well, yes, I'm going to explain it now, because I can explain it when it comes to statistical variability of this sort. So that's what I want to take a second to talk about. And we are getting a little bit technical, so I'm not going to drag you through all the math. It's in the book, and it's in a lot of statistics books as well. But at the end of the day, this ES that I showed you previously, and that we just pulled out of our own reasoning, is called the standard error. And it's related to the standard distribution of the sampling distribution of the stochastic variable. So I slipped that all in. It was a little bit complicated, but it's related to the probability. Any one time you take a measurement, what will you get? There's a maximum in the probability distribution, and then it's when it's has that well-behaved character that I was talking about. It has a symmetric probability distribution, and all the numbers kind of land in the vicinity of what we call the average, which is a good number to report for the measurements you're taking. But you don't always get the same value, which we didn't with the blood pressure numbers. So there is a very formal proof that of what this distribution is when you have a well-behaved random sampling of a distribution, that without anything systematic and untoward inside the process. And that is called the student's t distribution. And for the student's t distribution, 95% of the probability lies in the envelope under the curve that goes to the right by plus 2 times the standard error, and to the left by 2 times the standard error. So that's where that 2ES comes from. Now that 2 comes from saying you take a lot of samples. If you don't take a lot of samples, you better take you have to multiply the standard error by more than 2. And that's what this little table is telling you. So if you take 3 samples like we just did, n equals 3, you have to actually multiply it by a number that's closer to 4 than to 2. And that's an added, it's an added correctness when you use this distribution correctly. And it's a correction of this 2 that was used in all the previous calculations I talked about. So as I said, getting a little bit complicated, but I've got a worksheet for that. Okay, so here's the worksheet. I can put my 3 blood pressures in there. I can calculate the sample mean. I calculated it here with this Google Sheet, and the mean is just average of the 3 numbers. You can average the upper number, you can average the lower number. The variance, you can just use the built-in function var, which gives me the variance of these, which is related to trying to calculate this standard error. The standard deviation is just half of the variance, but you can also calculate it with a built-in function, etc. So this worksheet has the sample variance, the sample standard deviation, the standard error, which is derived in my book as the standard deviation divided by the square root of the number. And then you can calculate the blood pressure with its appropriate error limits. So the number that is my blood pressure from those 3 measurements is 108/86. I know the 108 plus or minus 12. I know the 86 plus or minus 3. They're not the same error limits. And now I have a good idea that in fact, my blood pressure is under 90, my diastolic blood pressure, which was the question I had. Actually, it was about the diastolic because the systolic was already a good number. It's under 120, even at the worst. Actually, it's right at 120. If I take 108 and add the 12, I'm at 120, which is fine. And both of them, it turns out, are fine. So that was a very quick tour of the mathematical stuff. But it's the 3rd type of error, that small random variations are a source of uncertainty. And we can use statistics to correctly assess how much uncertainty to assign to the numbers we measure. So those were the 3 types of measurements that I wanted to introduce to you: calibration, reading, and replicate. Calibration was associated with instrument or technique design, and most of the time comes from the manufacturer unless you calibrate it yourself, although there are some rules of thumb. Reading comes from interrogation of the reading itself and from the statistics that go into that. I have a worksheet for that. And replicate error comes from statistical effects or stochastic effects. And you'll notice that I've classified these errors as type B or type A. And I want to explain those. Those come from the Guide to Expression of Uncertainty and Measurement from the National Institutes of Standards and Technology, Washington, D.C. Used to be called the National Bureau of Standards. And that's part of the Department of Commerce in the United States. And it deals with weights and measures. So again, calibration and how accurate the devices are. When you go to the supermarket and they weigh your apples, you're trusting that they're not cheating you and that that device has been appropriately calibrated and is giving an accurate value. And it's being given an accurate value based on standards that are picked by NIST. And NIST categorizes uncertainties into these 2 general categories. Type A, which is the 3rd one I talked about, the random ones, where there's a very rigorous statistical pathway to figuring out what the uncertainty is and how to attribute it. But then there's also, as I showed, 2 and other potentially types of uncertainties that aren't related to random variation, stochastic variability, but they're very, very real. And such as the calibration and the reading errors. And these are arrived, and these are their words, arrived by logic, reflection, or experience. So you can see from the worksheets that I showed you that we used logic, we used reflection about what we were doing and how careful we were being, and we used experience to throw some things out and say, that's not important in this case. And that is not just me saying that it's okay to do that. It's really the way it is. that there are some uncertainties that we have to sort out ourselves with our common sense, and those are called type B. So the type A errors are actually much better covered in rigorous statistical books. And I wrote a book that's relatively rigorous about the statistics it covers, but it doesn't cover very much statistics. It is about uncertainty analysis in general instead. And I have a chapter each on calibration and reading error that are not mentioned in statistics books, and yet dominate as an engineer, as a practicing engineer, dominate a lot of the uncertainty that I actually deal with. And I would really like to drive a lot of practitioners back to the manual, which you can now Google up and get very easily, to see what the manufacturer rates the instrument as being capable of, because it may be that that's limiting the quality of your work. So just one more quick thing I want to show you, and that is how to combine errors. And I'm not going to do it in detail, but that's the other thing that happens, is that, first of all, there are 3 types of errors, even if you find 3 types of errors of the types I've indicated, and you need to combine those. And then also there are, you're going to take a number and use it to measure something. And so, for instance, this is a picture of a weighing analytical balance and a pycnometer, where a pycnometer is a highly calibrated glass device used to measure density. So you put a very precise volume of liquid in there and you weigh it, and the weight full minus the weight empty divided by the volume of the glassware gives you the density of the fluid. And this is state of the art. This is how this is done. But there's going to be uncertainty in the weights. You're going to subtract 2 weights. What's that going to do to the uncertainty? And you're going to divide by a volume, which, by the way, is a calibrated volume. So it has its own uncertainty. And you're going to divide by it. What's that going to do to the uncertainty? So that requires error propagation. Errors propagate through this technique of error combination, of number combination. And that's been very well worked out. That's in statistical books as well. And I do cover that as well. So we can think of this equation as some function f. This is the formal and scary equation for how to do error propagation. But this is really just the sum of, these are our friends, the standard errors of each of those individual devices. So we can take a calibration sheet and fill it out for the pycnometer. We can take a reading error sheet and fill it out for it's not really applicable to the pycnometer, but for the analytical balance. It also needs a calibration sheet. We can figure out what these errors are. The sort of ugly squared partial derivatives are not very hard. That's Calc 2. It's not that big a deal. And it can be built into a computer representation as well. So it's not that bad. So, and I also have a worksheet for this as well. So for the pycnometer case, again, I'm not asking you particularly to follow this, but you can take whatever combination of errors you like. You can take a measurement. So I would measure a full, measure an empty, measure know the volume, the 10 milliliter pycnometer. I can take the derivatives of this equation with some help if necessary to figure out what that prefactor might be. And I can use the worksheets to get those standard errors. Then I'm going to square these 2 and put them over here in the right. And these become things that we add here. See at the bottom that we add. And what's interesting about the worksheet pedagogically is that look at the numbers I'm going to be adding. I'm going to be adding 2 numbers that are 10 to the minus 11th and a third number that's 10 to the minus 5th. 10 to the minus 5th is 6 orders of magnitude higher than 10. These numbers are negligible. And there's some really good logic there. If I just made you take a calculator and do this, if you're a typical student, you would just do it and say, I hope I got that right. But you wouldn't maybe notice what you were adding. But using this worksheet, you can say, you know what, the uncertainty in the mass measurements is insignificant compared to the uncertainty in the pycnometer as it acts in the calculation I'm going to use it for. Okay. And so it's the pycnometer volume. So if you want a more accurate density, buy a better pycnometer. do not go by a better analytical balance. It's not driving the uncertainty. So by noticing what you're doing and organizing them up and saving them in a worksheet, you're building up your expertise in knowing how you know what you know. So in summary, we know what we know because we or others have observed the physical world, the empirical world, and thought about them carefully with careful measurements and made deductions about what the world is like and how it works. No matter how careful they are, there is no 100% certainty of anything measured. There is not. So we have to get used to the idea that there's uncertainty in measurements. And then, but it doesn't mean that all uncertainty means we know nothing. If we do careful analysis of uncertainty, as I've outlined here, we can say some very definitive things. And I just to go back one slide to say, we very definitively know that the accuracy of the balance is not driving the accuracy of the density. It's definitive. 6 orders of magnitude is not a subtle difference. So we can know some very firm things, even as we're uncertain about some of the details. So I've divided uncertainty into measurement, reading, and random error, and discussed those a little bit. Those are 2 different types of errors that are both very commonly present. And knowing the quality of our measurements helps us to think better about what we learned from the physical world. So that's the end of what I wanted to say today. These are my 3 books. My first book was on rheology. Steve introduced that's my research field. I wrote a book in 2001 called Understanding Rheology. I wrote a book on fluid mechanics in 2013, another topic I teach. And this is my 3rd book, Understanding Uncertainty Analysis for Engineers and Scientists. And I'm working on my YouTube channel, which is Dr. Morrison MTU. And I have lecture slides ready to go to work your way through the book. If anybody watching finds that this is something that they want to know more about. In a month or 2, there ought to be some more lectures on YouTube where you could get walked through some more examples in particular. So that's my story. Thank you very much.